Hello, guys. Hope you guys are doing well. Good evening, good afternoon, good morning, as per your different time zones. So, now let's start. Just once again, I will share my screen with you. Okay, guys. So, I guess you guys are able to see my screen. So, let me go to day 3 agenda. Yep. So, let's start with the day 3, guys. Now, so today we are going to talk about the different label ranges which are different on different Cisco iOSs. Then we are going to talk about PHP when ultimate hop popping. Last time around people were asking about that. And then configuration and operations of LDP on Cisco iOS and iOS XR. Today I'll show you the basic configuration of LDP, how to configure that on iOS and iOS XR. Maybe few of you guys aware of the basic LDP configuration, but if you guys are not able to, then I'll show you that today. Then introduction to MPLS L3 VPN, that also I'm going to cover. And the different L3 VPN concepts, VRF, MPBGP, route distinguisher, route targets. I'm going to explain all of them. Okay, so let's start, guys. So first of all, the different label ranges on different Cisco operating systems. So on Cisco iOS, 0 to 15 are reserved for special purpose. I will in further slides I will explain you what all those prefixes are. And then after that I'll show you, and then from 16 until whatever hardware supports, because guys, they limit the number of labels are actually based on the different hardwares. So from 16 onwards until the hardware supports, they that all considered as dynamic label allocation. Guys, just allow me 1 minute, just 1 second. Okay, so sorry for that. Now, from 16 until that particular hardware, the limit it supports, some supports 64K, 65K, some supports 1.3 million. So it depends on that particular model. So how many labels they support, that comes under dynamic label allocation. That is for Cisco iOS. From 16 until the hardware, 0 to 15 we cannot use. Then let's move to Cisco iOS XR before 6.1, means I'm talking about 5.2, 5.4 iOS XR. There 0 to 15 are again reserved for the same special purposes only. And then from 16 until 15,999 are reserved for static label allocation. Cisco iOS XR will allow you to do the static label allocation. You can statically assign the labels. So that is from 16 to 15,999. That is by default. But if we want, we can use that label range also for our label distribution protocols. But this is by default. After that, from 16,000 onwards until that hardware supports, that is called dynamic label allocation range. The dynamic allocation, dynamic label allocation actually is part of label switch database, LSD. That label switch database contains all the labels which is from 16,000 until the limit. That, and whenever a client come in who needs that label, so for an example, who can be the client? My LDP can be the client, my RSVP can be the client, my MPBGP can be the client, my TLDP can be the client, my OSPF or ISIS can be the client. So those protocols have to register them on LSD. Okay, let me take my pen. So we have something called LSD, label switch database, in which all the dynamic label, this database is actually contains all the dynamic allocation of the dynamic label allocation will be handled by the label switch database, and this you have to register yourself as a client to the LSD to get the labels. So who all can be the client? LDP can be the client. Okay, RSVP can be the client. MPBGP can be the client in case of L3 VPN. Your TLDP can be the client in case of L2 VPN. TLDP stands for targeted LDP. And your IGP can be the client. IGP only OSPF or ISIS. So these all are the clients for the LSD. So as soon as you enable any protocol of them, they will register themselves as a client to the LSD, and then LSD will start propagating the labels from dynamic label range. That is the story until the case of 5.2, 5.4 iOS XR. Then from iOS XR 6.1 onwards, okay, label ranges are a bit changed. So 0 to 15 again for reserved purpose. 16 to 15,999 is reserved for static label allocation. But now 16,000 to 23,999. This is reserved for some other purpose, that is called SRGB reservation. SRGB stands for segment routing global block. This label allocation only works when you have SRGB enabled, the segment routing enabled. Okay, so when you enable segment routing on the router, you can enable segment routing from 6.0 onwards. Okay, but in 6.0, when you enable, then only this label allocation will get reserved. But from 6.1.1, I guess, the from that point onwards, either you enable or don't enable segment routing, still that 16,000 till 23,999 will be reserved for sRGB. So I'm not going to get into this particular thing right now. We are going to cover segment routing, so I will show you that part when we are going to talk about the segment routing. So this is how the label allocation. Then from 24,000 until that hardware supports is the LSD, the dynamic label allocation, the labels, the part of the label switch database. So these are the reserved label ranges, okay, for different Cisco iOS, iOS XR, and their different versions. So now let's talk about the reserved labels. So we have 0, okay, which is reserved for IPv4 explicit null label. I will explain you, okay, which label is used for which different purpose. One is reserved for router alert label. 2 is reserved for IPv6 explicit null. 3 is implicit null. 4 to 6 we don't use, neither we use 4 to 6 nor or we use label 7, 8 to 12, 13, 14 we use if we are using OAM tools. OAM is your operation administration maintenance tool. So when we configure any MPLS based service, for an example, let's say L2 VPN or L3 VPN, so if we are using any kind of MPLS enabled service, MPLS based service, at that time we'll use OAM tools. Then 15th is the extension label, which is used for using the extension into the label header. So we are not going to get into there as of now. So the important one here which you need to know is this one, the explicit null label and the implicit null label. Okay, so implicit and explicit, they are clear by their names. Implicit is something which is automatically be used, and explicit is something which we have to make changes to do that. So let's proceed to the next slide, then I will explain you better about this. So now is PHP, penultimate hop popping. In next two sessions I was keep talking about PHP, but I didn't explain. So now I'll explain that what exactly the PHP is. PHP is a function performed by certain routers in the MPLS enabled network. It refers to the process whereby the outermost label of an MPLS tagged packet is removed by the LSR before the packet is passed to an adjacent LER. The benefit is that LSR has to do a label lookup anyways, and it doesn't make a difference whether this result in a label swap or pop. So however, the LER, this saves the one cycle of label lookup. So how this thing works, guys, just carefully see here. So I have, let's say this is my one router, this is the other router. So let's take phone. Now what happen is I have a prefix here, let's say X prefix. This is the prefix which is getting published in the IGP, and there is labeling which is going to happen for this X prefix. Now let's say label is already allocated. Okay, so when the packet is initiated, so last time around I was already explained how the control plane and data plane flow is. So when this particular user is sitting here, started sending the packet, and router starting pushing the, so this device, it will do the push operation. Okay, it will impose the label into the packet, send to its neighbor. This neighbor will do swap operation. So I already explained you what exactly the swap is. It will label come in, swap with the other label ID, send to the neighbor. Now this router do what? As I explained last time, this router again do the swap operation only. Okay. So when this router do the swap operation, so for an example, as I last time around I explained, 16 comes, it wipes 16 and assigns 17. Okay, but this is not actually happening due to the PHP. What is happening is this, how I get this 17. If you guys remember how I get this 17, 17 is my remote label. So how I get this remote label? Because this router has allocated, it's a directly connected prefix for this. So this router has allocated one local label, and that local label will be used as remote label here. So that local label, as he know that, see, this is my directly connected prefix, so why should I allocate a label for it? Okay, so instead of assigning the entire label, what this router will do, this router will send the label value of 3. Okay, this router will send the label value of 3 instead of any specific label, it is fixed. So when this router receives 3, what this router understands? This router understands that this is the last hope, the destination is directly connected to it, or this is the last router in my MPLS domain for this particular prefix. So what I will do, instead of swapping to the other label, when I receive the value 3, I automatically, it implicitly understood that instead of using any label at the remote label place, I will use pop. I will use pop. So when 16 comes, I will do the swap operation, but instead of using that label, swapping with a specific label, I will swap with the pop operation. Okay, I will put a pop label, pop tag at the label field and send it across. So now what happen when this router receives the packet with as an incoming pop label, so now he will not do label lookup. You remember last time I was explaining you that when a packet comes in with the MPLS labeled, I will do the lookup into LFIP, which is called label lookup. That okay, if this is the incoming, what is the outgoing label? Now, when he receives the pop label, it is understood that okay, I'm not going to use the uh, label lookup process. Okay, I will avoid that label lookup. I will not look into the LFIB. I know pop means this is directly connected to me. So just remove. So this actually, this swap operation, let me change color. This swap operation is actually referring the pop operation, because instead of swapping with a specific label, it will put a pop tag on it. So once a router receives a packet with the popped tag, he knows that, hey, I am the last hope for that. I am the last router for this destination. So if I'm getting pop, remove this and do a IP lookup directly and see where the destination is connected and send the IP packet to that destination. So what I am doing, so this is called ILER, Ingress Label Edge Router, and this is ELER, Egress Label Edge Router. So instead of doing two lookups on the egress, I have the option, I can avoid that label lookup and it will only do IP lookup. Okay, so this is called PHP, penultimate hop popping, where the second last router, okay, not the last router, for a specific destination, keep this thing in mind guys, for a specific destination, it does not mean all the time this router will do the pop operation. If the destination is attached here to this router, then this router will do pop operation for this destination. So it is actually based on the destination, that who is the second last router for that destination, that will do the pop operation. So that the egress LER, the my egress router will not have to do two lookups, it will do only the IP lookup. So I guess this thing makes sense to you. This is how the PHP works. This is the nature of PHP. It avoids the second lookup of the packet. Okay, it avoids the two lookups into the table by the egress LER. So that LSR, this router itself will do the pop operation. So this is when this router sends 3. Okay, when this PHP will activate when this router sends the label value 3. What you can do is that by the manual configuration, what you can say that instead of 3, which is implicit null, you can send label value 0. Okay, instead of, I removed that, sorry. So that last router, instead of sending 3, he will send 0. What is 0? Explicit null. Now this is not implicit, this is explicit. So again, clear by its name itself. Explicit mean to say he wants to make some changes explicitly. It is not implicitly, he wants to make some changes. So he will tell to the second last router that, hey, you do that pop operation. What actually he is doing in pop operation, he is removing that label value. Okay, that label tag. So instead of removing the entire label tag, if you guys have remember, in last time I explained you the process of the header of the label. So in that header of the label, we have one field called exp, which is known as experimental bit. So if I am using that experiment, so if I want to use that experimental bit, and there may be many reasons, I'll explain you. So I will say, instead of 3, I will send 0. So when I send 0 to this router will understand that, hey, I have to do, I will do pop operation, but instead of removing the entire tag, I will keep that exp tag in the label field. Okay, I will remove that label value. Okay, I will remove all the fields, that label field, the S field, the TTL field, but I will keep that exp field there. Why? Because that exp field is used for quality of service. This bit is used for QoS. So there may be reason that you are further doing some classification. When the traffic left the MPLS cloud, you are still using some classification, some marking, which traffic is already marked. So for an example, voice traffic is coming. How will you identify this is voice traffic? Based on the voice marking. So let's say DSCP EF bit, which is used for the DSCP EF marking, which is used for the voice traffic. So if the traffic is coming with the EF marking and it is marked in the experimental bit, okay, that marking is in that experimental bit. So instead of I can configure that this router, instead of sending that 3 value, saying that okay, remove that label and send me the pop, he will remove that label. He will send 0 value, by which he will remove the label but keep that experimental bit tag there, so that this particular router will keep the experimental bit left in the header and remove the rest of the fields. So again, there is a pop tag but with experimental bit. So what happened when 3 send? If you send 3, you will get pop tag in which no label will be assigned, no label field also. Okay, but what if you send 0? You will get pop tag, okay, plus exp, plus the exp field which is already there in the MPLS label. So you will get this, that exp will be used for further quality of service purpose. So if you are using that, you can use the explicit null label. Otherwise, by default it is implicit null. That mean to say, just remove the label and send me a pop tagged packet, so that I will understood this packet is destined for me. No need to do the label lookup. Straightforward, I will do the IP lookup and send the packet across. So I guess this thing makes sense to you. If you have any query, any question in that, just keep a note of it. You can discuss in the Q&A session. So guys, this is the lab topology, okay, which I am going to refer for this class and maybe tomorrow class as well, where we are going to configure the MPLS L3 VPN. So let me explain something about this topology. So I have one customer A, and other customer is customer B. So this is the one site of customer A, and this is the second site of the customer A itself. Then the other site of customer B, the first site of customer B, and the second site of customer B. This is the MPLS cloud. Okay, this is my MPLS core. But if you can see here, the customer A's first site network is 10.1.1.0. Okay, and customer B's first site is also 10.1.1.0. So both are going to come on this PE1. Okay, PE refers to the provider edge router. Okay, so this is provider edge router, this is provider router whose job responsibility is just to do forwarding. This device is called CE, customer edge router. So customer is sending same prefix by two customers, this PE is receiving. So he have to configure the VRF and all, which I explained you last time around. I will explain on the further more slides. Okay, it will create a labeled LSP from this PE all the way to this PE. Okay, so he will create a LSP, label switch path. Using that label switch path, he will send the customer's traffic tagged with the appropriate RT and RD. So I will explain you what that RT and RD, don't get confused in that. Okay, so that customer traffic will get landed here, assign the RT RD value using the LSP sent to the here. Using the RT value, I will get to know that for the which customer is it, and based on that I will forward the traffic. Okay, so this is how the things work. Their job responsibility is just to do the switching based on the MPLS label. where these devices will have much more job responsibility, because your LSP will be initiated and terminated here. You have L3 VPN. I'm going to explain you about the L3 VPN, so you don't need to get confused right now. So your L3 VPN will be terminated and initiated here. Okay. After that, the VRF tagging is going to happen on these interfaces. So I will show you guys. If you can see my topology, if you can see my topology, I have mixtures of iOS and iOS XR and iOS XE. So these are my XR boxes. Okay, and these are my XC boxes. So I will use XR as a PEN as well as P, so you will get to know the how the configuration is bit different. Few of the you guys are maybe aware of that the configuration on iOS XR, but if you guys are not aware of the configuration on iOS XR, I'm going to show you in the further more slides, and I'll show you practically as well. So maybe by in today's and tomorrow's session we'll do practical lab, okay, in which we will configure the intra AS MPLS L3 VPN. Okay, so let's proceed further with the different MPLS L3 VPN concepts. So first of all, the LDP configuration on iOS XE. So I'm not getting into the L3 VPN part. I'm just showing you the configuration. So you don't need to worry from the configuration side, guys, because I will do the entire lab in front of you over the session. Okay, maybe tomorrow, in which I will set up a L3 VPN, configure LDP on iOS, iOS XE, iOS XR, and you will get the different flavors of it. Okay, so this is a sample configuration on iOS XE. If you want to assign the label range, some of the organizations are using this, some of the organizations not. If you are using it, recommended action is that all the device should use same label range. Okay, so that you will not get confused. But if you are making different label ranges, it's okay. So 100 to 200 means I told you that I have a ranges of label. Okay, but I am using 100 or 200 to 200. 0 to 15 is something which I cannot use. After that, I can use any of the label value, even though it is already reserved for some purpose, but I can still override that. So I'm using 100 to 200 label value, so that the labels will getting allocated from 100 to 200. So if you want to get more granular control on top of your MPLS network, so that how the labels are getting allocated, you want to have the more control on that, you can specify the range. Okay, so using that range value, what happen is that based on those range values only labels will be allocated. Then assigning router ID, you can assign router ID for LDP. Okay, so you can assign by use of this command also. Sometime you need to use force keyword after this. So what happen is, if a LDP has already picked up as an interface IP as your router ID, okay, if MPLS already picked up the any interface IP address as a router ID at that time, and you want to change that, so you can change that by the use of this command. But sometime it will not come in effect, so you have to do it forcefully. Okay, so and but the main part here is that whatever interface you will allocate as a router ID in the LDP, that IP address of that interface should be reachable from your neighbor, should be reachable from your adjacent device. Okay, this IP needs to be reachable, because based on this IP reachability only, LDP will make the neighborship. Okay, so I've already explained you LDP is using TCP and UDP port 646 for their internal transmission, but the neighborship is based will be based on this particular interface IP reachability. Then how to configure? Just go under the interface and use MPLS IP. That's all. We in last 2.5 days we are just discussing how the MPLS forwarding take place, label allocation, LDP operation, everything. But at the end, how the all these things will get configured by the use of just one command, which is MPLS IP. As soon as you enable MPLS IP, it automatically enables the LDP, because that is by default. Okay. Now the verification, how you can do verification, I didn't put much commands here. Okay, that I would like to show you when we do actually practical. So this is the just the neighborship command. So if I highlight the main points here, so this is the neighbor's IP. You can see port 646 is used. Okay, and this is the source IP address which I am using to send my packets, and this is the destination IP address where I am sending the package. So my source interface is 646, destination interface port number is 14172. So it will be a random port number, it can be anything. Okay, so same vice versa happens. This is on the other side outputs, this is the one side output. So this connection, if I go back into my topology, this neighborship is actually in between of those two devices. Okay, so you don't need to worry about the configuration. I will say this is just the outputs. I will configure each and everything from scratch in front of you while doing the practical. Just keep your questions, guys. I will have a Q&A. At that time you can ask your questions. Okay, at the end of the session you will get time to ask your queries. And this is the message, guys. This is the log message which you will get. Okay, so this is the interface. LDP has started. After that, negotiating the hello packets, they will neighborship has been config make up, and this is the neighbor's ID and the status of neighborship. So my neighborship is up for last 2 minutes, so that means to say it is stable. If it is fluctuating, you can see the fluctuation in the timers as well. Now this is the LDP configuration on iOS XR. If you can see, the configuration on iOS XE is just this much. That's all. Go under the interface, enable. So it's either iOS XE or iOS, both are same. But in iOS XR, it is quite different. So iOS XR is actually, guys, hierarchical in nature. Okay, iOS XR is quite different from iOS XE or X iOS. Okay, why? Because this is hierarchical in nature. So there you just go under interface, enable MPLS. Here you need to go into the MPLS and then enable interface in that. Okay, so if you can see, I go under one hierarchy, that is MPLS IP. Inside of that, I have specified router ID. I enabled this is for IPv4 traffic. I enabled all the interfaces which I want to enable, and then at the end and commit. So instead of going on in the individual interfaces and then coming back to the config mode and assigning the router ID, you can do all whatever related to MPLS at one context, under one context. So this is the reason behind the hierarchical nature of iOS XR. So you don't need to get into the multiple context. So I will explain you the configuration on iOS XR, and iOS XR is quite different. So maybe in further more session, if I get the time. Okay, so I will highlight the iOS XR features also, the kernel architecture of iOS XR, the image file of iOS XR, how it is different. It is more over the process oriented. So for your information only, iOS XR is more over process oriented operating system. Each and every service, each and every application which is running on iOS XR, it is actually running as a process. So you will have the ability that you can stop a process, you can start individual process, you can upgrade individual process. Like you can stop BGP, you can start BGP, so it will not affect OSPF. So all processes, not all, but most of the processes are independent from each other, so they will not interrupt each other. So let's say for example BGP is not working, there is some bug in the BGP. Okay, so bug is something which you can usually get. So if there is a bug in the BGP and it is not working as expected, so what you can do is that you can individually shut down the BGP, individually restart the BGP. If BGP needs to get any upgrade, a small patch upgrade, you can upgrade specific process also. So these all things you can do on iOS XR. So let's see if we get the time. I'll spend one session on the iOS XR in which I will explain that part also. Verification again, show MPLS LDP neighbor only. Output is quite same. The my outgoing interface, neighbor ID, and the port number, the random port number. So downstream unsolicited. I already explained. In iOS XE, it won't show how the label allocation is actually happening, but in iOS XR, you can see the label allocation is happening downstream unsolicited. So if I check the neighborship detail of RSVP, which I'm not using right now, I will use it later on. So if I will show you the neighborship status of RSVP, it will be downstream on demand. It should not be downstream unsolicited. Now let's jump into the MPLS L3 VPN concept. Okay. So today I guess I can only cover up the L3 VPN concepts and the overview and different components of this. And maybe in tomorrow's session, we are going to have the hands-on lab on L3 VPN. So MPLS layer 3 VPN use a peer-to-peer model that uses BGP protocol. BGP is the only protocol which is used in MPLS L3 VPN. So you will have end-to-end PE to PE L3 BGP session, and that BGP is the special purpose BGP, I can say, will use MPBGP. Earlier, the MPBGP was used only for the L3 VPN. Nowadays, MPBGP is used for some other purpose. Like for an example, Cisco ACI is also using MPBGP, and we can use in SDA we can use MPBGP SDA, software defined access. So we can use MPBGP there as well. So nowadays we are having much more applications of MPBGP, whereas earlier it was just the L3 VPN. This highly scalable peer-to-peer model allow enterprise subscriber to outsource routing information to the service provider, resulting in significant cost saving and reduction in the operational complexity for enterprises. Service provider can then offer value-added services like QoS, traffic engineering, allowing network convergence that encompasses voice and video and data traffic. So, guys, basically, what earlier happening, I'm talking about before the L3 VPN, we need to dedicate one PE for one customer. We cannot use same PE for multiple customers, because if they are coming out with the same private IP subnet, I don't have the option to segregate that. So then that L3 VPN components come, the concept of L3 VPN has come, and using that, we'll have multiple ways to resolve this issue. So whereas where I was allocating dedicated PE routers for the customer, now I am dedicating one PE, a big huge router, maybe ASR 9K or something, and for catering multiple customer, multiple services, and even on top of that I can provide the value added services like the providing traffic engineering, bandwidth allocation, QoS. I can converge my network more granular for voice, video, and data traffic separately. So, what are the different components by with the we are going to play around? So, different components is VRF, MPLS, and MPBGP. These are the three things which we need to set up our L3 VPN. So VRF is virtual routing and forwarding. I already explained you. It will create a separate routing table for each and every customer. So what happen is earlier one routing table. So when we are getting same IP subnet, both will be clashing into the routing table. So VRF will give us the ability so that we can create a dedicated routing table. Okay, get my words, guys. dedicated routing table for a customer, so that whatever prefixes are coming from that customers are catered into that particular VRF routing table. So instead of getting into the global routing table and having the clashes, and we can have the one single routing table. Okay, and but VRF offer us the individual routing tables for individual customers. Okay, so we are using different kind of taggings for that, and we'll use that. Then we use MPLS, multi-protocol label switching. So MPLS is the underlay, okay, which will be used for the label switching. And then we'll use MPBGP as the overlay, okay, which will forward our VRF enabled VPN enabled packets, L3 VPN enabled packet, I should say, from one side to the other. So let's see. Let's talk about the MPBGP header first of all. So guys, before going here, let me go back to my topology and explain you few of the basic components here. So customer A sending the prefix 10110 advertising towards PE. So let's say customer red only. So right now I'm talking about only the customer A, the red customer. So what he will do, that top of 10110 he will add a value called RD value. Okay, so I'm mentioning here RD. So same way, when the blue customer comes in and advertising 10110 same network, he will add a unique, the different but RD value. But guys, this value is unique locally only, doesn't need to be unique in entire network. So when I get the prefix from customer A, I'm getting 10110 red RD. I'm getting the traffic from customer B, I'm getting 10110 blue RD. Okay, so they are segregated. I have a different routing table called red for this customer, and I have a different routing table called blue for this customer. Now what happen is, this RD value make the router unique, this particular prefix unique locally. Then I will add one more value on top of it, that is called RT value, route target. RD value is route distinguisher, and then the other value is RT, route target. So route RD value, you would do what? Locally make the route significant, unique. Okay, and make a unique routing table for that. So that is job done by the RD. Whereas in RT is used for remote site. So this is the prefix which will be created. Okay, this is the actual packet, the update, which MPBGP. So MPBGP session is between PE to PE. PE to PE will be MPBGP, multi-protocol BGP. Okay, this MPBGP will carry this particular packet, because this packet is, because see, this is your normal IP header. Then I'm adding more two values on top of it. Okay, so this packet is actually become more, the size of the packet get increased. The values I will explain on the furthermore slide. So the size of the packet is bigger. So MPBGP is the only protocol who can carry this big packet, okay, and send from one side to the other. So that's why the MPBGP is the right now is the only, not right now, I think so I'll going to be also, this is the only option which can be used in the reference or in the context of the L3 VPN to carry this big frame, okay, this big packet, and will get landed here. When this packet get landed here, you have IP, your IP prefix, you have RD value, and then you have RT value. So what the receiving router will do, it just discard RD value. Okay, it's just straightforward discard the RD value and the receiving end. But see, still he is sending, but at the receiving end it will discard, because he's saying, hey, it's your property, it is your value which you are using to make that route locally significant for you. I have nothing to do with that. I will look into the RT value. Okay, that RT value basically do what? That RT value will define where is the destination, because here also there are two VRF routing table. One is red and the other one is the blue one. So whether to send this packet in red or blue is based on that RT value. So we will export RT. I'm just taking example X. Okay, I'm exporting X from red VRF, and I'm exporting Y from blue VRF. So I need to import Y in blue VRF, and I need to import X in red VRF. Okay, so this is how the communication is going to be. And these router, based on that X and Y value, which is RT value, route target value, it will send the packet either on red VRF or blue VRF based on the received RT value and the configured import value. So what he is exporting will be imported here, and vice versa. What he is going to export will be imported this side also. So this RT value will make remote communication, send the packet into the appropriate VRF, and RD value is used for internal purpose, okay, for making route unique internally. So this particular packet is sent through MPBGP all the way to the other side. Now the other thing, this is the RD and RT value concept. I guess it makes sense to you. Now what happen is, when an IP packet comes in and get into the VRF, and I have configured MPBGP session, okay, between those PE to PE. So what your packet will do, inside of your packet, it will add one more header. So this packet will contain your original source and destination. That additional value will have the source as PE1, okay, destination as PE2. So it will look for the label of PE2, okay, on this router. So I should be having the label for PE2 from my neighbor. Okay, so based on the labels forwarding for PE2, the your pack, see, this is MPBGP is the direct relationship from PE to PE. In between you may have hundreds of devices, so your traffic is not going to send on the air. Okay, your traffic has to have the physical media, you have to have the data path. So that data path is going to be this. So this is your data path. Okay, and this data path will be forwarded based on your MPLS label for remote PE. So if the label is missing in between of your MPLS cloud, your MPBGP packets will not get delivered. So your customer may not be able to reach the other side. So when this packet reach here, it will wipe out the additional information. Okay, the label information and all will be wiped out, and original IP packet it will look, and whatever RT value it receive, it sent to the VRF, and then it, based on IP forwarding, reach to the appropriate destination. So this is the guys concept of L3 VPN is, and how it is working. So I guess so you guys, this thing has make sense to you. So let's proceed further. This is the MPBGP header, guys. I have already explained you how the header is. This is your IPv4 for prefix 10110. Then this is RD value. This is the format. There are different type of formats also, which I will show you in tomorrow's session when we do the practical lab of it. So 1:1 is the format, is the RD value. This thing is called VPN v4. Okay. So VPN v4 is actually the type of the additional community agency or address family into the BGP, which we need to enable to send this packet. Okay, so this is your 4 bytes. Okay, and this is 8 bytes. So this is your 32-bit, this is 64 bits. So your VPN v4 itself is a 96 bits. So none of the protocol can carry 96 bits packet. It has to be carried by only MPBGP. Then on top of that, you have 64 bits, 8 bytes route target value also. Okay, so you can see route distinguisher and route target can be different. Route distinguisher and route target can be different because this thing will be used locally. This is local, and this is for remote side. So when the packet received from the remote and at the receiving end, it will discard this. This value will be discarded. We'll look into it, see which in which VRF I'm importing this value. So I have to, from the sender end, I have to export this, and on the receiving end, I have to import this. So I will see in which VRF I'm importing this and will send the packet on that. Then there is one field called label. This is not your normal LDP label, which is used for the forwarding. This label called service label. This label is called service label, which is assigned in our case by MPBGP. Who is assigning this service label? MPBGP, which will I use for the identification of the service. My battery is going to die. Just give me a second. Okay, guys, done. Sorry for this. So this is how this is the entire MPBGP header. So I, on the day one, if you remember, we have something called outer label and we have something called inner label. Outer label is known as transport label, and inner label sometime it will be a service label, sometime it's a transport label again, but I will explain you in what cases. Right now the inner label is the service label and outer label is the transport label. And the transport label, the outer label, is assigned by LDP in our case as of now. I will explain the different scenarios where it will be assigned by the different protocols. And the inner label, which is service label, which is assigned by MPBGP in our case as of now. Okay, so the outer label will be looked first when there is no outer label, because you know when it reached to PE at one hop away, this label will be popped off, so there is no label. So when it received to the egress PE where my VPN, the L3 VPN is getting terminated, I will be able to see only this label. Okay, service label. So based on that, I will identify the type of the service. So I will show you tomorrow in the practical session how the labels are allocated, how we can see where the inside inner label, where is the outer label. I'll show you that. And guys, that L3 VPN is having two parts, intra AS and inter AS. Okay, so how the intra AS and inter AS is, so I guess I stripped up the images. This is intra AS. So what we are going to configure tomorrow is intra AS, because your service provider is having one AS. Your service provider is in one AS. Okay, this is one AS. So this is intra AS VPN. Then if for an example, as I took on the day one, I have a site in Singapore and the other site is in US, California. So none of the service provider can cater that long way. From Singapore to California, there is no one service provider who can cater. So I have to take services from the different service provider. So I don't need to take, basically I will subscribe to one service provider. There also I will subscribe to one service provider saying that, hey, my other site is US, just provide me the connectivity. So now this is service provider's job responsibility to get collaborated with some other service provider, maybe one or more than one, okay, and provide me the connectivity from Singapore to US, okay. And that furthermore, service provider, maybe one AS, maybe multiple AS. So this is my Singapore, and the other site is in LA, for an example. So from Singapore to LA, they cannot, one service provider cannot cater the complete end-to-end path. So ISP1 is catering in Singapore, ISP2 is catering in LA. They have the collaborated link between them. And now if I want to create a L3 VPN from here all the way till here, that is called inter AS L3 VPN. Okay, this is called inter AS MPLS L3 VPN. That is between two different AS. It is crossing the boundary of two different AS. So far so good. Does it make sense to you? So this is how the inter AS and intra AS is. Okay, so right now we are going to focus on intra AS. Later we will focus on the inter AS. In inter AS we have different options to configure it. This one I can say it quite complicated compare to intra, but I will try to explain both of them to you. Okay, so that's all for today, guys. Okay, tomorrow we are going to set up this practically on iOS XE as well as on iOS XR. So guys, now time for Q&A. Let me know if you guys over the chat if you have any question. Yes, Morris, any question you can post over the chat. Morris, you can see my last video there. I explained the label assignment in detail. So it's available. I will send you the link. Okay. Can we use same RD for two different customer? Locally, no. Smriti Bhushan, we need to have the unique RD on the local for each and every customer, because RD value is actually making the differentiation between two different customers traffic, so it has to be unique. Simple definition of VPN v4 address. So VPN v4 address, we can refer that IPv4 prefix with the unique RD value is a VPN v4. That's all. So IPv4 plus your RD tag is VPN v4. Any other question, guys? Okay, so I'm expecting good. So no much questions. Okay, that means for a single customer we can use same RD in two different PEs. Yes, in two different PEs you can use same RD value, no problem, but it has to be unique locally. RD is a locally significant value. So as many customers you have, as many VRFs you create, you should have the different RD values for them. Okay, so I'm expecting no more questions here. Okay, guys. So hope you have liked the session. Okay, I will show you Amar's lab will do tomorrow. Okay, so I will explain regarding the lab setup tomorrow. Hope you have liked the session today, guys. See you tomorrow, same time. Bye. Same time tomorrow, Maris. Okay, guys. Bye. Have a nice evening, nice day.